Other than that, let's start with this. So in chapter 2, we deal with motion in one dimension, either horizontally or vertically. In this chapter, we combine both, but we first need to review the whole idea of displacement now in terms of a vector r, where r, if you are on the plane, will have two components, the x component and the y component. So you can have a particle going from position A to position B, and that's the displacement delta r, where r final minus r initial will be the displacement, and r is basically the vector sum of the x component and y component respectively. So you can have x initial, x final, y initial, y final. So there it is, right? R final minus R initial. And again, R is a vector with two components. You can also define velocity by doing delta R over delta T. And also the whole concept of instantaneous velocity can be applied by using the derivative of R respect of time. If they give you R as a function of time, of course, which is actually very common. Right? So the average velocity will be the displacement over time. So it's the same equations now. Instead of delta x, we use delta r, right? R is the notation that we use in physics for a position vector, right? But why we don't use delta p? Because delta p is actually another variable that we're going to use, which is momentum. So r is the one that we use for this. And if we use the derivative or we just take the limit, right, we get the instantaneous velocity. And the magnitude of the velocity, the speed, is just the magnitude of the vector v. So again, as you can see, depending on which position you are, now you are not in a linear sort of motion, right? So let's say you're giving a curve. We know that the slope, the tangent to the curve on a position versus time graph, was the velocity. So if you're giving a function and you want to find the derivative at any point, you can actually draw a tangent line in a given point in a curve, like they show you there. So that's how they find VI and VF, right? It's a tangent to the trajectory that is given by the dotted line. So now we have the velocity vector and the final and initial velocity vectors. So since they have different directions, we can compute the difference between both if we use the graphic method that I show you in chapter 3. And it's given there on the right. The other way you can see this is that each tangent has its own slope, which is different. So that means that even though those vectors look the same length, so you may have that the speed is actually constant, but it's changing direction across the trajectory, which we want to see more in a circular motion. That change on direction is what creates an acceleration. Because it gives you different velocity. You can have the same velocity, you can have the same magnitude in a different direction, 2 I meters per second to j. So you have a difference on velocity. And you know if there is a difference on velocity respect on a given time, you have an acceleration. So that's how you can produce an acceleration, by having a change on direction, or as you know, a change on the magnitude of the speed. So that leads to this question. If you are in a car and you know you have access to the brake, the gas pedal, and the steering wheel, what will make the car accelerate? By the way, when I talk about accelerate, it can also be a negative acceleration. So it also means slowing down. So what do you think will cause acceleration? Obviously, the gas pedal, right? When you accelerate your car, and the brake. But as we know from the previous example, and probably you experiment this in the highway or when you are driving, whenever you steer, your car will change speeds. Or even if you are trying to keep the same velocity, the whole change of direction will produce some sort of acceleration. How do you know? Because your body leans to one side. And we know that's called centripetal acceleration, which we are going to discuss in this chapter. So even though you try to keep it constant, you have an acceleration there. That means that the free controls will give you an acceleration. The whole concept of the change on direction comes from the whole idea of vectors. So just to show you very quickly, if you are going with a car, this, let's call it 3R meters per second, and then you change it to minus 3J meters per second, even though the magnitude of the speed is the same, the acceleration, the vector acceleration, is the final velocity minus initial velocity. Let's say this happened in 1 second, okay? So over delta t. B final is minus 3J. B initial is 3R. It's not going to be 0. So the acceleration is minus 3J minus 3I meters per second squared. Obviously, if you find the magnitude, if I want to find the magnitude, that will be 3 root 2 meters per second squared if you Pythagoras. The direction of the acceleration will be that 45 degrees respect to the vertical, or 45 plus 180 is 225. So, I mean, that's pretty much, it makes sense, right? The acceleration will be. So, that's a whole idea of changing directions, all right? We've noticed, that's what I was talking about, R is a vector that has two components, X and Y components, right? So we're using the unit vectors there. So again, motion in 2 dimensions can be modeled in the X and Y axis. When we start doing the projectile motion, you will see how this pans out. And you won't need to memorize any new formulas. There are new formulas that I'm going to show, but you don't really need them. If you understand the whole idea of motion in the X and Y axis, you will be more than fine. Now, this is very important because, as I said, the vector position is R, but R is xi plus yj. So you take the derivative on each component, keeping the unit vector there because it's part of the solution, and then you get Vxi, Vyj. So in my horizontal velocity and a vertical velocity. If you take the derivative again, what do you get? You get the acceleration, right, on x and on y. So you can write the equations of motion that we had before now in two directions, right? Because V is Vx final, Vx initial, and A, whatever is on x, you have to keep it with x. So here you see, right? X with x, y with y. The same with this equation for constant acceleration, though. You can create both in x and y. So you have acceleration on x, acceleration on y, and then you can do this. Right? It's probably better to keep it separately. So basically, you have in x, you have in y, and then you have it like that. So you don't get confused. And then you can just have R final equals to R initial plus the initial times time plus 1/2 AT squared. Remember that for constant acceleration, you can use both equations. That's fine. All right. There are some graphical representations in there. Again, that's more to show you the addition of vectors. So it's more relevant to the vector type of, for the vector chapter. But again, let's emphasize that you can use the equations that you see on the top there of the slide only when the acceleration is constant. Okay, here's what I wanted to get. So let's do a problem where you are given different directions, all right? So it says that you have a particle moving in the xy plane, starting from the origin at t equals to 0. And it says that the initial velocity has an x component of 20 meters per second and a y component of minus 15 meters per second. The particle experiences acceleration in the direction x given by that. Find the velocity at any later time. Okay. So you can draw a graph. I want to draw it, but eventually, unless it's something that you strictly are required, if you keep your values and variables, let's review some of those equations, right? It was 20 and negative 15, right? So you can have from the origin on the x and y axis, 20 meters per second to the right and minus 15. Yeah, it's sign. Even though just by pointing down, you know it's negative. And the acceleration is an acceleration on x of 4 meters per second squared. Actually, I. Or I, right? Let's see, I want to see the suffix. Yeah. All right. The velocity initial, or the initial velocity, is 20I minus 15J meters per second. And the final velocity, or the velocity at any later time, is V initial plus AT. So let's not forget that equation. Well, plus or minus, right? But it's accelerating, so we use a plus. The initial is this. So we can write that. 20i minus 15j plus 4i or 4ti. Now, I with i's, j's with j's. So I with I, 20 plus 40 I minus 15j. That is the velocity at any point as a function of time. Now we want to find the velocity and the speed at t equals to 5 and the angle the velocity makes with the x-axis. All right. So for t equals to 5 seconds, the velocity will be 5 times 4, 20 plus 20, 40i minus 15j. So that will be the answer. To find the angle, if you remember from vectors, we did that before, use that the tangent of theta is minus 15 over 40. We know that the angle has to be the second quadrant, right? Minus 15 over 40. Wait. 40, it should be in the fourth quadrant, right? Because it's 40 here and minus 15. Well, let's take a look. We have to do the arctangent of that. If I use my calculator, I get minus 20. Okay, let's suppose that this is a good example of this. So let's say I get right here. Let's say I get a vector. So, let's say I get that vector. And the angle I'm giving in the calculator is minus 20.6. So a negative angle is this. Right? Normally the angles are counterclockwise, but clockwise, that will be like below the x-axis, that will be minus 20.6. You can say that's the angle, or you can declare the angle on the fourth quadrant, which will be all this. That will be 360 minus this angle, 339.4. So this angle will be at 339.4. And just draw it and show it as well. Remember, this was this velocity here. That's right. Oh yeah, how do we get the speed? The magnitude of this, right? So the magnitude at t equals to 5 will be the square root of 40 squared plus minus 15 squared. And if I do my calculator here, I'll get 43. Okay, so I will probably start with example to show you how things now can be changed in two directions. As I said before, right? This is a chapter where we are going to be reviewing some of the previous concepts, right? Velocity, acceleration, speed, and the equations, some of the equations of motion. Okay. All right. So that example is also in the slides. Now I'm going to expand on it, and I want to try to find the position of the particle as a function of time. All right. We need the equation of position, R final, equals to R initial plus V initial times time. We have initial plus 1/2 squared. So to find that, we will need, I will erase that. I'll just leave the initial speed and I'll write the equation of motion for V final. We will leave it for X final, for R final, sorry. So R final equals to R initial plus V initial times time plus because it's positive there, 1/2 acceleration, yes, in meters, right? Now we know our initial is the origin, so this is 0. The initial is that, so 20I minus 15J, okay, with times time plus 1/2 of the acceleration for I t squared. Again, i's with i's, j's with j's, so R final 20 plus 2i, so 20 plus 2 t squared I, right? The I is like a variable. You cannot, and the thing is a t, sorry, t is a variable. So you cannot combine, but it's a expression there. There's no j there, so just minus 15j. That's your equation for the position as a function of it. And the thing